So yeah, as Seth said, I'm Patrick Lewis. I'm a PhD student at University College London and Facebook AI Research. And I'm going to talk about a recent paper that we've put onto arXiv recently, which is retrieval-augmented generation for knowledge-intensive NLP tasks, which is work with a bunch of folks at FAIR and some at NYU, Ethan Perez in particular, ex-FAIR intern. Yeah, so I want to get started by saying the kind of first observation is that pre-trained language models are great. That's not a controversial statement. And specifically, these general purpose seek-to-seek pre-trained models that we have now are getting really powerful. So T5, BART, GPT-2, and even GPT-3, really useful models. And they kind of have these interesting properties that they capture world knowledge in their parameters. And they have strong results on a load of different tasks. And most importantly, I think they're applicable for almost any NLP task. You can very easily just take BART or T5 and fine-tune it for the task that you want to do. So classification you can do seek-to-seek things, you can do translation, all sorts of stuff, easy to do with a seek-to-seek model. But they do have some downsides. So they hallucinate and sort of make up facts that aren't true about the world. And whilst they do have world knowledge stored in their parameters, they often struggle to access and precisely apply that knowledge for a task that you're interested in doing. And they can be difficult to update. So as you train a model, it's great and it knows a lot about the world, but when you finish training it and the world changes, the model stays the same. So it doesn't update its world knowledge as the world around it changes, which is a bit of a problem. I'm just going to put a pointer on. And on the other hand, we have this other observation that we've seen recently, that retrieval is a really useful tool. So externally retrieved knowledge and text is useful for a huge variety of different NLP tasks. And it's really one of the most precise and accurate ways we have to access knowledge. So if you want to learn something, you go to Google and you use an information retrieval system to get you information from a big index that you can use to answer your problem. So it's really precise and a really excellent way of accessing knowledge. And also it's trivial to update at test time. So once you've done training a model, you can just add new documents to your document store that you retrieve from, or remove documents or edit them. And there's this third interesting line that's been coming out recently of these dense retrieval models, these trained retrieval models, these neural retrievers, which is starting to outperform traditional information retrieval systems, which is really exciting. So maybe it's the time to take another look at retrieval and see how we can integrate it into our models. But there are other issues, of course. So if you are going to learn a dense retriever, you need to have labels to supervise your retrieval system on. And you may not always have labels to train your retriever on for your given task. And if you don't have labels to train your retriever for, you need to rely on heuristics, what I'm calling heuristics-based retrieval. So hope that for your task that you want to retrieve documents for, TF-IDF or BM25 work well. And often they aren't a great fit, or they'll work okay, but not super well for the thing you're interested in doing. And then finally, if you're going to incorporate retrieval into your model, you need some way of integrating your retrieval system into your downstream model itself. And this is usually some kind of task-specific architecture thing that allows you to do this for your task, but doesn't necessarily transfer to other tasks. These models are kind of difficult to play with and experiment with. So we wanted to investigate whether we could combine the strengths of explicit knowledge retrieval and these powerful seek-to-seek models. Before I dive too deeply into RAG, our model, I just want to highlight a few related works. I won't go into a lot of detail here, mainly for the interest of time, but we do want to sort of say that these are important works, and we're heavily inspired by a lot of them. And you can refer to our paper for a more in-depth related work section, or check these works out yourself. And so RAG is very much a kind of successor to a model that came out last year from Google called Realm, which has similar ideas about trying to integrate retrieval into a pre-trained system that can be used for downstream tasks. And RAG is a slightly more general version of Realm that you can generate from rather than just use to extract spans for question answering for. Another line of work that we're super interested in is lines of work that try and assess how much knowledge is stored in the parameters of pre-trained language models. So the Llama probe from Pretrained et al. 2019 and a related work from AKBC that we've just been through, highly related to this area. Full disclosure, I'm an author on these papers, but these works try and assess, like how much factual knowledge is stored in the parameters of pre-trained language models. And more recently, this concept of closed book question answering. So if you have an open domain question answering task where you have natural language questions, maybe factual questions about the world, traditionally what you do is you retrieve documents and then you extract answers from those documents. And in closed book QA, you just try and directly generate an answer from a pre-trained language model. So you fine tune a language model given natural language questions to generate answers out. And those answers can only really be stored in the parameters of the language model itself, or maybe it's question answering training data. So this is an area we're kind of interested in. This idea of parametric memory or parametric knowledge stored in the parameters of a language model. And then RAG models kind of have a connection to works like memory networks or memory augmented neural networks, since we have this big document store that we're going to explore, which could be considered to be a big neural memory. And then finally, there's relations to knowledge grounded dialogue models, which for a given chat history, you can often augment the chat history with related information or retrieved information that can help you generate better responses for chatbots. There's other related works as well, but I'll stop now in the interest of time. Okay, so what is a RAG model or a retrieval augmented generation model? So we have these three properties that we kind of want to access for a RAG model. We want models that can jointly learn to retrieve and generate in an end-to-end manner. And we want to do that with latent retrieval, i.e. we don't want to need labels for our retrieved documents to train them. We just want the documents to be some kind of a latent property of the model, so we don't have to worry about them. And that allows us to have this general recipe for any seek-to-seek task. So any task where you might think of applying T5 or BART or any sequence-to-sequence model or encoder-decoder model, you could drop in a RAG model as a simple replacement, and everything else would remain the same about your training loop or the things you try and do. There's just magically behind the scenes, it's going to retrieve documents from its store of documents and use them to produce better outputs. Cool. So to achieve that, we need kind of three components. We need a pre-trained generator model, which given some textual input will be able to generate some textual output. So we could have any kind of sequence-to-sequence model, language model, left to right language model for this. So you could imagine GPT-2 or T5, GPT-3 if you have a ton of resource. But we're going to choose BART just as a kind of reasonably sized model that performs well and is a general purpose useful model. You also need something to retrieve documents from a store. So we use a pre-trained retrieval model that what you can use for an input sequence of an input text to retrieve a document. So we use dense passage retriever, which is from a recent paper from FAIR entitled Dense Passage Retrieval for Question Answering, I think. But you could use other things. You could train models using the inverse close task or some other kind of pre-training method to do a differentiable retrieval. And we'll talk a little bit more about this in a minute. And then the third thing you need is actually your store of text documents. So you need an indexed knowledge base of text documents. So indexed is something like that, a phrase that means you want it to be able to do fast retrieval from it. And for this, we use Wikipedia, but you could also consider something like Common Crawl or a big pile of tweets or any other thing. It could be scientific papers, some big text corpus of documents to retrieve from, which you think will be useful to do your downstream task. And yeah, so RAG models, we considered them to be models that combine parametric and non-parametric memory. So I mentioned parametric memory briefly before. So parametric memory is kind of knowledge that's stored in the parameters of a pre-trained language model, specifically in the generator of our RAG models. And non-parametric memory would be knowledge that's stored in the non-parametric memory, so in the knowledge base, in the indexed knowledge base of text documents. So RAG models combine these two types of knowledge, and because of that, they can work really well for what we call knowledge-intensive tasks. So these are kind of tasks that you can imagine that you wouldn't expect a human to be able to do without access to a big set of external evidence themselves. So something like question answering, where you might need access to Wikipedia yourself to find the answers to given questions, or things like that, maybe fact checking, things that are really knowledge intensive that you can't expect humans to do without like a massive amount of like learning to be able to do well without access to external knowledge. So without further ado, here is the RAG architecture. So we have input sequences that come in, input text sequences that come in. And those text sequences get fed into our retriever module. And in the retrieval module, a neural network will take the input sequence and encode it as a query vector. And then we perform maximum inner product search to find documents in our document store, which are represented by document vectors. Find the documents which have the highest dot product with the input question. For these top K documents, in terms of inner products with the input question, we retrieve those top K documents, and then we pass them into the generator model, the BART model. And then for each document, we feed it through the generator, and we produce a prediction of what we want to generate. And then finally, we marginalize over those top K documents to finally produce our output sequence here. Okay, so now we're gonna dive in slightly more. So we have two types of RAG model that we propose in our paper. We have what we call the RAG sequence model, and then the RAG token model. And they have the same idea, but they differ slightly in how they go about producing an output. So both models are trying to estimate the probability of generating an output sequence given an input sequence. So this could be a question, and this could be an answer, for example. And how RAG sequence works is that for a given input, you first retrieve documents here using the retriever, and then for your document, you feed it into a generator along with the question, and you produce an output sequence, or you produce an estimate of the probability of generating the output sequence given your latent document and your input X. And then you marginalize at sequence level, so over the entire Y sequences. Whereas in RAG token, you still have the same components, the retriever and the generator, but this marginalization is happening every token you generate here. So we have the input X, we retrieve document Z, and then we produce the next token Y, given the input document X, the latent document Z, the input X, latent document Z, and a partially decoded output sequence Y. So yeah, they're both different ways of estimating the same thing, which is the likelihood of generating Y given X. And we train both of these models by simply minimizing the negative log likelihood of generating output sequences on input sequences. And all you need to train a RAG model like this is input sequences and output sequences. So it could be like machine translation, or it could be question answer pairs, or it could be claims and the label of whether they are true, false, or you can't tell. So it's very, very flexible. So you can use this wherever you'd use, say like BART or T5, anything where you have input and output sequences. Okay. Diving into the components, we have the dense passage retriever. So the DPR retriever is a bi-encoder architecture, of what some people refer to as a Siamese network or a two-tower network. And essentially how it works is that you have the log probability of retrieving document Z given the input X is proportional to the dot product of a document representation vector and a question representation vector. And these two vectors come out of fine-tuned BERT models. So to use a retriever in RAG, you need to first get a pre-trained bi-encoder that works relatively well, or like can do some kind of basic retrieval. So we just grab the dense passage retriever from the dense passage retriever paper, And that's been pre-trained for natural questions and trivia QA. So for an input natural question, the DPR model is pre-trained to retrieve documents which are likely to contain answers, which makes it sort of like a bias towards doing quite well for open domain QA, but it's still general in that you can, later we'll show how you can fine tune this retriever for any kind of downstream task that you have. So once you have a pre-trained bioencoder, you then want to build your Wikipedia or your document index. And this is something you only need to do once in the whole life cycle of a RAG model. So only ever happens once. We've already done it. When we open source the paper, we'll release the index. And so what we use is Wikipedia documents. We use 100-word chunks from Wikipedia. And we have 21 million of them. And we feed them into our document encoder to get a document vector for each of our Wikipedia documents. So 21 million vectors, which we then put into FICE to build an index so we can do maximum inner product search very quickly. And then when we train RAG models, we back propagate into the query encoder of the RAG model so that the model learns how to retrieve better by adjusting the query vector for a downstream task. We keep the document encoder fixed at this point because otherwise we'd have to rebuild the document index every time we send gradient updates to the document, to the BART document encoder, which would be super expensive. So people have done this in the Realm paper, they do it at pre-training time, but they don't do it at fine-tuning time because it is very expensive and you'd need like hundreds of TPUs to do this well. So you don't need to do this. This whole RAG model will work on a single GPU if you have some time. Okay, moving on to the generator. So we said before that this is BART. If anyone's not familiar with BART, it's a big pre-trained sequence-to-sequence model. So it works a little bit like BERT, but instead of being a masked language model where you have an input sequence which has words masked, you have an input sequence which is noised somehow. And rather than predicting the identity of words that have been masked, you try and generate the clean sequence using this transformer encoder decoder. It's generally quite similar to T5, but I think the training procedure is a bit more simple, and it seems to perform slightly better than similarly sized T5 models, but the jury's out a bit. But you could use any generator here as long as it's a model that can estimate the probability of an output sequence from an input sequence. So BART, T5, you could use GPT-2 as well, or GPT-3, but we use BART. And the way we incorporate the latent document Z and the input X when we're trying to produce an output sequence is simply by concatenating the text of the input document, of the input query and the latent document together as a single long string, and that gets fed into BART. Okay, so now we know how RAG models work, and we know how to train them. We need to know how to decode from them at test time. So the way you decode from the two different RAG models are slightly different. For RAG token, it's very straightforward. You can just do standard beam search with the following transition probability. So basically, because you have access to these per token distributions here, you can just plug this into a standard beam search solver or any kind of natural language decoder system. So you could use top K sampling, all that kind of good stuff that people do when they generate sequences from sequence-to-sequence models. The RAG sequence is a little bit tougher to generate from because the model can only give you probabilities of particular sequences. It can't generate them word by word, conditioned on all the documents at once. So the way this works is if you imagine we have a RAG model and we retrieve the top 3 documents. So for an input X, we retrieve the top 3 documents here. And then the way we decode from RAG sequence is we first, for each input document, generate an output sequence using standard beam search, using the BART model for each input document here. So imagine we now have 6 hypotheses, 2 from each latent document. Then we run forward passes to estimate the probability of generating that hypothesis from a given input document, from a given input and latent document. And then we repeat that, and then we multiply by the probability of retrieving that latent document. And then we do that for all of our hypotheses. Then we can marginalize out the latent document to obtain our probabilities of generating our specific hypothesis here, given our input X. And then we simply take the highest, or like the best scoring one, as our actual generation. So this process is a little bit slow, and you have to do quite a lot of forward passes here. So you can make a very rough approximation here that the probability of generating a sequence is 0 if it wasn't obtained through beam search for that particular latent document. And this allows you to do fast retrieval using RAG, fast generation using RAG sequence with only a small drop in accuracy, or almost no drop in accuracy. Okay, experiments. So yeah, moving on to experiments, I'll reiterate the fact that you can use RAG models to any task with input and output sequences. So it can be anything where you have input text and output text. And that output text could be weird. It could be in the form of like parsing stuff, or like structured things, or it could be classes, as long as the input is text and the output is something that could be a sequence or a single token. But we also want to focus on tasks that have a clear need for precisely accessing knowledge, because we know that like BART and T5 work really well on a ton of tasks, but they don't do so well on things that really need accurate manipulation of knowledge. So we focus on a number of knowledge intensive tasks. So the first of those is open domain QA. So we look at 4 standard open domain QA tasks here called natural questions, trivia QA, web questions, and curated trek. And the task here is, given a natural language question, return a short 1 to 5 word answer to that question. And how you go about doing that is up to you, but most methods involve a kind of pipeline of retrieval, and then some re-ranking, and then all kinds of stuff. And then you extract an answer out from your retrieved text. Or there's the closed book QA, which I mentioned briefly before, where you simply take the input question and try and directly generate the answer sequence. We also look at an abstractive open domain QA task. So because RAG can generate output sequences, like whole sentences, generating short answers is not that interesting. So we also look at a kind of open version of MS Marco, where you have input questions in the same way as open domain QA, but your outputs are full sentence answers. We also explore question generation. And here we try to generate Jeopardy questions from Jeopardy answer entities, which is fun, that we'll look at in a little bit. And then finally, we look at fact verifications. We look at the FEVA dataset, which is a collection of claims in natural language, and then whether they can be supported or they're refuted, or there's not enough information in Wikipedia to tell whether that claim is true or false. So that's a kind of fact checking or fact verification task, and as a classification task rather than a generation task, just to see whether RAG is general enough to work in classification settings as well as sequence generation settings. Okay, going to open domain QA performance, we have some closed book models here, which I mentioned, and open book models. So for closed book models, we have T5 11 billion, which is really big, like crazy big model, very, very difficult to run or like have the hardware to work with. And then we have a variant of it trained with salient span masking, which is a kind of approach to make it, it's a pre-training objective to try and make T5 better at answering questions. And you can see it does reasonably well at natural questions and trivia QA and web questions. And then on the other side, we have open book approaches like Realm and a pipeline of the DPR retriever and a traditional re-ranker extractive answering question answering model from the DPR paper, which represented the state of the art at the time of writing RAG. And here are the results of the RAC models. So we obtain state of the art in 3 of these tasks by quite a margin for natural questions and web questions and curated trek. and do really well at the closed book comparison trivia QA split here. And we kind of want to make the point that RAG models kind of represent a hybrid of the closed book and open book models. So closed book models rely entirely on parametric knowledge to answer questions. And open book models rely primarily on non-parametric knowledge, the retrieval-based knowledge to do their work. But the RAG models can do both. So they kind of get the best of both worlds, and we think that's why they perform so well. So yeah, to sum up there, strongly outperforming closed book models, even ones with specialized pre-training, and these vast models, they're like 11 billion parameter models, and RAG is like a 1/10 of that, maybe less, 20th of that number of parameters can still do really great results and outperform them. And we don't need a cross-encoder re-ranker. So we don't need to do re-ranking and expensive modeling in a pipeline approach. And we don't need a span extraction head to do well at open domain QA like the DPR model did. So what that means is that most open domain QA models retrieve text, and then you extract a contiguous span of text from the model as the answer. And that's usually considered to be like a big, helpful inductive bias for the model, and much easier than free-form generation of answers. But we actually find that generating answers free-form it results in better performance. And like maybe two reasons why this is that documents that don't contain exactly the correct answer, so you can't extract the answer from it, but they may contain like clues to help you generate the right answer. And that's something that RAG models and similar things can take advantage of. And then, yeah, we can also answer questions correctly, even when the correct answer is not in any of our top retrieved documents and in our conditioning documents. That happens at about 10% of cases, which shows that like parametric knowledge is still useful for this model. It's kind of enjoying the best of both worlds. Okay, here's an example, if it wasn't clear, of how open domain question answering works. So you have an input question here: who sings "Does He Love Me" with Reba? And the gold answer here that you're supposed to return is Linda Davies. And the RAG model produces Linda K. Davies there, so that's nice and correct. Whereas BART, if you trained a BART model to do this, it would hallucinate an incorrect, but like plausible sounding answer of the Beatles, which you can kind of imagine is a high likelihood in general response, but isn't specifically correct given that input question. Moving on to the abstractive open domain QA, so the MS Marco task. This is the one where you have input questions and you need to generate an output full sentence answer. So we've adapted MS Marco for this. So MS Marco is a data set of queries put into the Bing search engine and 10 passages, one of which will contain an answer to the question and a correct sentence answer that you're supposed to generate out. And so usually what people do is they build models that will take the input question and condition on one of these passages and then generate the output. But sometimes you really need access to that gold passage to generate the correct response. And so if you were looking at an open domain version of this, where you throw away all those given gold passages, you sometimes can't generate the response that the data set is looking for. So for an example, there'd be a question like, what's the weather like in Volcano, California? And the answer they're looking for is, oh, it's 71 degrees Fahrenheit or something. And you can't do that unless you know that like on a specific day, that was the weather. And in one of the passages, it contained the weather for that day. So you'll never perform as well as a state-of-the-art model, which uses gold context like this one here. But we are able to see that RAG strongly outperforms a BART-only baseline here. And it's actually not too far away from state-of-the-art models. So if we look at the Rouge long and the blue one scores, RAG models are doing better than BART and actually aren't too far away from state-of-the-art models which have access to this gold passage. So to illustrate this a bit more, here's an example question from MS Marco: how many calories in average apple? And it's kind of written in classic search engineese language, which is why it's not super fluent. It's just something someone's typed into a search bar. And BART generates this response, which maybe looks okay at first glance, but I'll read it out and you'll realize there's maybe some problems with it. The average apple contains 1,000 calories in an average apple and 1,200 calories in a medium apple. So you can see that there's two basic problems here. It's a bit repetitive and not really nailing the task, but then also it kind of makes this hilarious gaffe where it's saying there are 1,000 calories in an apple, and that's not factually correct at all. If you look at what BART generates, RAG generates for this input, you can see that it says there are 126 calories in an average apple, while an extra large size apple has 172 calories. So we see two things. One is that it's much less repetitive, but then it also has a much more sensible estimate for the number of calories in the model, the number of calories in an apple. The gold response here was an average apple contains 80 calories, which, okay, that's also a fine response. But if we look at the top document that was retrieved by RAG from all these Wikipedia documents, that top document stated that a typical apple serving weighs 242 grams and contains 126 calories with a moderate content of blah, 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 blah. So you can see that actually RAG's response is probably more factually correct given Wikipedia than the response from some random web page that was the golden annotation for MS Marco. So RAG is getting the answer correct here, despite having not a very good match with the gold response. So that's kind of like a typical thing that you'll see for this data set and a typical example. Okay, so moving on to the third thing, Jeopardy question generation. So if anyone's not familiar with Jeopardy, I think most people will be familiar with it. It's a format, like a quiz format, where you have, traditionally you're given a fact about an entity, maybe it's slightly cryptic, a very specific fact about an entity, and what you're supposed to do is guess the entity from the clue about the entity. So in this example, Florida's in the southeast corner of the 48 contiguous states. This state's in the northwest corner, and from that information, you're supposed to guess that it's Washington. So what we want to do to really test the generation performance of RAG models is actually flip this around. So that what we want to do is input the Jeopardy answer, which is Washington, and then train models to generate Jeopardy questions. So we want train models to generate responses like this gold one here. And if we do that with BART, we can see it generates something that looks like this. So this state has the largest number of counties in the US, which seems reasonable, but is actually completely factually incorrect. It's hallucinated. It looks correct, but it's wrong. Whereas RAG will generate, it's the only US state named for a US president, which is in fact correct about Washington. To give another example, we have the Divine Comedy, which is a work by Dante. And BART actually does know a bunch of stuff, so it does have useful stuff in its parameters. I don't want to put it down. So it generates this pretty impressive response. This epic poem by Dante is divided into 3 parts: the Inferno, the Purgatorio, and the Purgatorio, which is reasonable, but again, it's had some problems with repetition, and it hasn't got the last work from the Divine Comedy correct. Whereas RAG is even more specific, because it says this 14th century work, so it knows the century of the Divine Comedy. And it says it's divided into 3 sections: Inferno, Purgatorio, and Paradiso, which is correct. So yes, so Jeopardy question generation constitutes a really challenging, knowledge-intensive generation task, which is really difficult. Very, very interesting, like test bed for these types of models that do knowledge-intensive generation. And we actually found that unlike most of our other tasks where RAG sequence tends to perform best, RAG token was performing best for this task. And we think that's because often Jeopardy questions incorporate sort of 2 facts from different documents. So in order to do well, you'll have to generate an output question where you've used facts from 2 different documents that you retrieved. And this is much easier to do with RAG token because it generates per token. It can condition on different documents for each token it generates. So here we have the blue 1 scores and a variant called question blue 1, which has higher correlation with human judgments. And you can see that the RAG models perform better than BART. And then we also ran a human evaluation because this is quite difficult to do with automatic metrics. We ran a human evaluation where we asked assessors, we showed them an input entity and 2 generated Jeopardy questions from it. And we asked them which one they preferred. If they preferred A, they preferred B, or they thought both were good or both were bad. And we asked them to assess the factuality of the generated questions, and we encouraged them to use the internet, use Wikipedia to check whether these generated facts were true or false, and the specificity of the generated question. So whether the question could only refer to the entity it was generated from. And we can see like a very strong preference for RAG here in terms of factuality and specificity over BART. And this is three-way annotated as well. Okay, so I want to take a slight detour here to talk about the interaction between the parametric and non-parametric memories. So I've mentioned these before, that the parametric memory, the knowledge stored in the parameters of the BART generator, and the non-parametric memory, the knowledge stored in the documents in the retriever. And we wanted to know how these two types of memory kind of interact with each other. And so this little example maybe shines a light on how this is working. So here what you're seeing is a figure that shows the posterior distribution over documents as RAG token generates a response. So here we've inputted for Jeopardy question generation the answer entity Hemingway, and the RAG token model has generated the output Jeopardy question. The Sun Also Rises is a novel by this author of A Farewell to Arms, which is factually correct, by the way. But you can kind of see that there's a really big spike for document 2 when the model is generating The Sun Also Rises, and a really big spike for document 1 when the model is generating A Farewell to Arms. And if you look at the documents retrieved for the model, so this RAG model retrieves five latent documents. The only document to mention A Sun Also Rises is document 2. And the only document to mention A Farewell to Arms is document 1. So you can see that when it's generating The Sun Also Rises, document 2 is having a big effect on the generation. And when A Farewell to Arms is generated, document 1 is having a big effect. So you can kind of see like how the facts are being taken out of the document and then placed in as it gets generated. But you can see that the effect only lasts for that first important token from the title of the book. So the is fine, it's not super interesting, like most books start with the, but it's the word sun that really like says, okay, I'm generating this title, The Sun Also Rises. And so this sun is document 2 is very important for producing the token sun, generating the token sun. But then after it's generated the sun, the distribution flattens back out. And it seems that no document is particularly dominating the generation here, which kind of suggests that the BART model kind of knew The Sun Also Rises was a book, and that once it started to generate it, it was totally fine completing the rest of that title. It didn't need the documents to do that. And you can see the same pattern really here for where it generates an A, which is a less common starting token for a book title. And so document 1 is really needed for the generation of the token A. And then after the A is done, the distribution flattens out pretty quickly as well. So going even further with this, we think that the retrieved documents are basically queuing the correct responses from BART, kind of prodding it in such a way that the BART model can better use its parametric knowledge to generate things. So it kind of intervenes specific tokens, and then the BART model does the rest of it. We can kind of show some evidence for this by, if we feed the BART model with the input Hemingway and the partial decoding the Sun, a BART model that's just trained to do Jeopardy question generation, so not a RAG model, just a BART model that's trained to do Jeopardy question generation, will complete this partial decoding. The Sun Also Rises is a novel by the author of The Sun Also Rises. So it does actually know The Sun Also Rises is a book, and it is by Hemingway. It's just that maybe it can't generate it itself without requiring a document to kind of cue it into doing that. And so like you can do this again, pushing it further. So if you feed a BART model trained only to do BART only model trained to do this Jeopardy question generation with the input Hemingway and the longer partial decoding, The Sun Also Rises is a novel by this author of A, the BART model will happily complete it, The Sun Also Rises is a novel by this author of A Farewell to Arms. So it does know that after A, the best thing to do is generate farewell to arms. So it doesn't need the documents to do that. BART knows that, and that's stored in its parameters itself. But it really needed a document to kind of force the generation of this token A. Otherwise, it would have generated The Sun Also Rises again, which is a repetition and bad. So this is kind of maybe giving us a clue about how RAG models work and why the retrieved documents are useful to generate better responses. So we can also look at generation diversity. So this is like how diverse and interesting are the responses from different models. And we look at this for our 2 generation task, our MS Marco and Jeopardy question generation task. And you can see that RAG models generate much more diverse responses than BART in both of our tasks. So there are more distinct trigrams, so like more distinct, different, diverse language being generated by the RAG models and the BART models. And that's mostly because the BART model is repeating things quite a lot, or repeating the same generation for different inputs, whereas RAG is much more diverse and specific. Okay, moving on to the Fever fact-checking task. So here, I'll put all this on the screen. So for Fever, you have a claim, a natural language claim about the world. And then it's associated in the task with a class label, one of 3 classes. The claim is either true, according to Wikipedia. It's refuted according to Wikipedia. The claim is not true according to evidence in Wikipedia, or there's not enough evidence in Wikipedia to tell whether the claim is true or not. So there's these three labels. And in the Fever data set, evidence is also like annotated in Wikipedia that shows you where evidence exists in different Wikipedia articles to say whether the claim is true or false. And it's done at the level of a sentence. So they can give you sentences at training time that tell you whether a claim is true or false. And so most models build in these complex pipelines that first try and retrieve a Wikipedia document and then try and extract evidence sentences. And then from the evidence sentence and the claim, do some kind of NLI type thing to finally produce a final result about whether something is true or false, or not enough info. Whereas RAG, we can train it simply on the claim and the label pairs. So natural language claim goes into RAG models, and then you train it to just end-to-end produce refuted, not enough info, or supported at the end. And by doing this really simple training setup, you can actually get within 4% of state-of-the-art models, which are, as I said, really complex pipelines that use strong retrieval supervision and a ton of heuristics and other bits and pieces, which we don't need to do. So that's nice. I mean, it's not as close as I'd like, but it's kind of encouraging for the future of these types of approaches that are end-to-end learning to retrieve their own evidence for proving whether something is true or false. And then finally, we also look at a two-way task where we only look at the subset of Fever where we have claims that are either true or refuted, so supported by Wikipedia or refuted by Wikipedia. And here we compare to a Roberta model, which is trained, which is given access to the gold evidence sentence. So the Roberta model is classifying based on the claim, concatenated with a gold evidence sentence, both at training and test time. And it kind of represents an upper bound of how well you could expect a Fever model to work at support or refuting. And RAG, which isn't given the evidence document at all, no evidence is given to train RAG. It learns to retrieve its own evidence, only performs about 3% worse than this Roberta upper bound on this two-way task, which I think is quite exciting. Cool. So a final thing that we can consider doing, I mentioned right at the start that it's very easy for a non-parametric model or a retrieval-based model to update the facts about the world as the world changes. So you can add documents or remove documents to your index, which is a big benefit of this type of model over something, say like a pre-trained, fine-tuned T5 model, which you need to or that you need to fine tune again when your data set changes a bit. And even more so, like say a pre-trained model was trained in 2016, it will contain a lot of knowledge about the world up to 2016, but it won't know about things that have happened since 2016. That knowledge won't be stored in its parameters. But potentially a RAG model can be trivially updated. So we wanted to check whether this was indeed true. So what we did was we took a 2016 Wikipedia dump and a 2018 Wikipedia dump. And we built two indices, two Wikipedia indexes from it, two knowledge sources from it. And then we built this little time-sensitive question answering data set of world leaders who had changed between 2016 and 2018. So for example, between 2016 and 2018, the president of Peru had changed. So the answer to who is the president of Peru was different between 2016 and 2018. And so we evaluated RAG using the 2016 index and the 2018 index. And we found that when we evaluated it using the 2016 answers, the 2016 answers, it got strong performance, 70%, which is good for this type of model and this task. And indeed, when we used the 2018 leaders and the 2018 index, it did almost as well, 68% doing well. But when you had a mismatch of the leaders and the year, performance was poor, which is exactly what we want to see. So basically, you can take this one RAG model and plug in different document indexes into it, and it will change the behavior of the model to make the model think it's in 2016 or think it's in 2018 based just on the index, which is a fun result as well, and something that really shows some of the benefits of this type of modeling over something like just a big T5 parametric model. Okay, so one of the last things we did is we did some ablations over the retrieval setup of RAG. So the first thing we ablated is whether we fine-tune the retrieval. So I said earlier on that gradients get back propagated into the query representation of the bioencoder of the retriever. So RAG can learn to retrieve things as you fine-tune it, can learn to better retrieve as you fine-tune. So to see how well this works, we try what we call RAG frozen models, where we don't backpropagate evidence, don't backpropagate gradients into the query, into the retriever at all. And we see that retrieval fine-tuning is always helpful, even when the retriever itself had been supervised for a given task. So you can see that it makes a big difference, say for natural questions, to use backpropagating into the retriever as opposed to not backpropagating into the retriever here. Even though the model that the retriever we initialized from was already pre-trained to do well at natural questions, fine-tuning the model in the RAG, fine-tuning the retriever in the RAG framework improves it even more, which is a cool result. I really like this one. And then we also explored whether a BM25 model, so like a really optimized BM25 system, which is a fixed sparse-based retrieval, a little bit like TF-IDF, but with highly tuned parameters, would outperform, how that would perform. And we find that the maximum inner product search, like the learned retrieval, the bioencoder retrieval, usually outperforms BM25. The only exception is fever, where BM25 is slightly better, which is an interesting result, and it's good to have something to work for. We think that's because there's a lot of word matching that's needed to go from claims to the evidence in fever. Just the way it was annotated makes that a very effective strategy to match words between claims and evidence documents. And so that like sparse word matching is really helpful for that kind of thing, that the bioencoder or the MIPS retrieval is a lot more kind of soft in its word matching, but more kind of semantic. So maybe a hybrid approach where you did an ensemble of BM25 retrieval and MIPS retrieval would work well there, which is something that would be perfectly feasible with RAG. We just didn't do it. Okay. So finally, next steps. So the things we want to do next is we're working on open sourcing, because I know there'll be hopefully questions about that if people are excited about this. So we're open sourcing this right now, and we're working with Hugging Face to get it into Hugging Face. So it should be pretty easy to clone from Hugging Face transformers and just play with. The DPR model, which is like a component of RAG, is already in transformers, so that helps us with our efforts. We hope to have this out in the next couple of weeks. So RAG should hit transformers at some point, which is something we're excited about. And there'll be more on that later. But then there are a number of aspects of RAG that we want to improve, and we actually now have people looking at. So one problem we had with RAG models for some tasks is that if your initial retrieval results weren't useful at all, so the top K documents you retrieve for a given task were entirely unhelpful at the beginning of training for a task you're trying to do, often what would happen is that the gradients that the retriever received would be really bad, like terrible gradients. And you'd get this problem we call retrieval collapse, where there's no good retrieved document at the beginning, so the model can't learn what a good retrieved document looks like, so it never really learns that behavior. And instead what happens is that the model will learn to retrieve the same document regardless of the input question, which is unfortunate, because then if it's retrieving the same document regardless of the input, you're never actually going to learn any more retrieval, so your learning process stops at that point. So we want to investigate ways to make more robust retrieval, that this won't be a problem for, like more exploratory, maybe taking ideas from reinforcement learning and create exploration-driven stuff. We're working now at multi-hop reasoning as a way to bring that into RAG models, because right now they can only do a single hop of retrieval before producing outputs. And like better retrieval initialization. So we use DPR initialization for our RAG model, but that by no means is the only way to do it. You could use all kinds of different retrievers. So that would be something interesting to look into. And then like ideas that you could think about is multimodal RAG models. So like, what if your document store is actually made of images or something else, or structured stuff? These are ideas we're really interested in exploring. And then things like maybe we could train RAGs end-to-end as a pre-training task. So if we can imagine some pre-training task that we could pre-train the whole of the RAG model on, that would be cool. And that kind of connects to some work that's come out recently, like the Marge model, which is quite similar in some respects to how RAG works, but has different maybe aims. Okay, that was my spiel. I'll say thanks for listening, and I'll now take a look at the, how do I?
You have 8 questions in the Q&A. You have 1 question in the chat, and I did post in the chat the URL for your paper, and I noted that it includes your email address in the paper if people want to follow up with you. So go ahead and field the questions.
Okay, cool. Let's take a look at the Q&A. Can I provide any references to work on capturing real-world knowledge via the seq-seq models? So generally, it's a result that these pre-trained models capture real-world relational knowledge. So if you look at the paper, I think we cite Pretrained et al. I think I mentioned it briefly, so that work was done for just BART models, but the principle would be the same. I haven't directly assessed how well BART, for example, can capture real-world models, real-world knowledge itself, but you could run the Llama probe on it, and it would probably do similarly to BART. I know that T5 is pretty good at this, just because it's very good at this closed book QA stuff. So you know that it's capturing lots of knowledge in its parameters because it can learn to answer questions correctly. So that knowledge has to already be in the parameters for it to be able to learn these mappings. So yeah, I would take a look at closed book QA work. That's the first question. Question number 2. how is document encoder built using BART? Unit of measure is document instead of word or query. So the document encoder is using the class token of the BART model. So I don't know how familiar different people are with the fineries of BART, but BART has a class token first of all, and then the input sequence for the rest of it. And if you're interested in classification, then you can just take the representation of the class token, and then that's your representation at the top. So that's your document representation and your query representation. That's how you can turn an input sequence into an input vector, into an output vector. How does the dot product between query and an entire document work well for dense retrieval? Maybe I didn't explain that well. So like the dot product is between a query vector and a document vector, and it's pre-trained by DPR to do that well. So that's something maybe you can look at the DPR paper, which you can find via our paper if you want to find the citation, to see how well that works. So it's a kind of learn retrieval thing.
We have Gabriel enabled to speak. I'm sorry, if you're done that question, he can ask his live.
Okay, cool. Yeah.
Hey, Patrick, this is a really great talk. Thanks. I had a couple kind of related questions. So the first one I posted, I think you answered, was, is there a danger that the generator could still hallucinate if the information required was not returned in the retriever step? I think that's when you were talking about retriever collapse.
Yeah.
So it got me interested. It seems like in this scenario, the generator is mostly, I mean, there's still some knowledge stored in the parameters, but it seems like it's doing a lot of work in just forming a coherent sentence from the knowledge in the non-parametric memory. Two kind of sides of that coin. One, do you think this opens up a world where you can use a language model that wasn't trained on 100 TPUs, that just doesn't need to know facts, but knows how to create reasonable language from facts? And then on the flip side of that, have you thought of a non-parametric memory that's not a text corpus, like something like a knowledge graph?
Cool. So yeah, so the first part of that is how powerful does your generator need to be, I guess.
Yeah.
And so I guess, so yeah, we used BART large. I don't know exactly because I haven't tried with other generators, but there are some results that came out really recently that actually like do much better results on open domain QA than our model does. And they use T5 base and T5 large. Both, I think T5 base is smaller than BART. And so like, you know, in terms of fine tuning those models, it's pretty light in resources. Like you can do it on a single card for a couple of hours just to fine tune one of those language models for your use case. So if you're only interested in like taking an existing model and fine tuning it for something you care about, you can totally do that. In terms of whether you could train your own from scratch language model in this kind of setup, in theory, yes. I don't know how well it would work in practice. You might get some like instability stuff. But yeah, it'd be interesting to try. And the second part of the question was about whether we've thought about something that's non-textual as the knowledge base. So we didn't do this, but I think that's really like something that should be looked at, and I think is relatively likely to work well. Because a lot of people have structured knowledge, and structured knowledge is in some ways easier to retrieve, or like easier to retrieve it, and in some ways harder. So learning to retrieve like triples from a triple store, and then conditioning on them to produce outputs, that would be cool in a kind of end-to-end differentiable way.
Yeah. I
think that's really interesting. A couple of people have mentioned that to me as a cool thing, but yeah, I don't know if one will appear from some lab somewhere in the next few months. Who knows? But yeah, I think that's a promising direction.
Yeah. Just a super quick follow-up. I think it would be really interesting to see questions of the form, how many calories does a pink lady have, and see if it can make that jump.
Cool.
Pink lady is an apple has, even though You know, those are, I don't know if that's multi-hop or if that, even if the fact Pink Lady wasn't in there, the reasoning step of this is
Yeah,
an apple has this many calories.
I think that would be really cool.
Let me check that you have a question from Ruby. Does ontology have any role in these? An ontology, for instance, would be one way of capturing that a Pink Lady is a variety of apple. You know, maybe you jump to that question. Ontology, any role? What state?
Yeah. So it totally could do. You can imagine having the ontology as encoded as some triple store again that we were talking about. Like your knowledge base doesn't have to be just a big pile of text. It could be structured. It could be semi-structured. It could be, like, I guess you could have different types of ontology. You could have like terms and then definitions, or you could have like a proper like hierarchical thing. Pink Lady is an apple. Apple has X calories. I think it would be really cool to get, like, I think the ultimate goal for something like this is a model that can retrieve relevant structured, semi-structured, and unstructured information, and together learn to retrieve all of that useful stuff, and then can sort of absorb all of that information in some way and summarize as an output. I think that'd be really interesting. So yes, I'd say it definitely does, just future work. Cool. Should I take, so I can answer Scott's questions next. Is Scott on the line, or should I just answer it?
No, he's not. Michael McIntosh, I will enable to speak after you're done this question with Scott, Scott's question.
Cool. So yeah, it's a good point that Scott raises. So the question was, is it easy for RAG to report metadata so that its answers can cite references? So yes, like one thing we look at in the paper a bit is that we look at the retrieved documents and treat them as a kind of post hoc explanation of why a particular answer appeared. So because the model conditions pretty strongly on the retrieved documents, you can kind of say that they're almost causing the output answer. It's not quite as simple as that because it can choose to ignore them. It's kind of a soft thing, but you can certainly treat them as what people call provenance in the explainable AI literature. So you say like, oh, why did you say the answer was this? And you can say, oh, I'll just examine the documents you retrieved about why you said that. So in the example about the apple that you sort of said like, oh, it has 126 calories. Why did it say that? And we were able to look at that document that was retrieved latently and say, oh, like it said that because Wikipedia says in this little passage that it retrieved that there were 126 passages. So you can use that as like as a pretty good assessment of provenance or explainability slash references. Cool. So yeah, is Michael ready to ask the question?
Yep. Yeah, I answered my question earlier. It was accidentally skipped, I guess. So basically my question is, in a system like this, it's always going to find a match, or very frequently going to find a match. How do you handle the situation where it shouldn't find a match? I've worked on a previous QA system, and one of the big problems is it always gave the best answer, even though the best answer might have been a terrible answer. So in that system, we offered a gambit of like, well, I don't know what you're asking me, but here are some questions that I do know answers to, or could you rephrase your question? So how does your system cope with something like that? And how do you train it to cope with something like that?
Yeah, it's a great point. So I guess that's currently something that you can't easily do with RAG. So the closest I can come to is that the fever task that we talked at near the end. You have these input claims that can either be supported, refuted, or not enough info. And that not enough info class is a little bit like saying, I can't answer your question. But it wasn't actually that good at doing the not enough info part. Like it wasn't super good at, if you can imagine intuitively, it's difficult to retrieve something for something that cannot be retrieved because there isn't enough info to answer it, or it can't be answered. So it's not super easy. I know people explore this in contextual question answering, where they produce, they're actually like questions that deliberately cannot be answered or should not be answered. because they're misleading, and the models produce two things. They produce a probability of there being an answer, and then a probability of what the answer is. And only if the probability of there being an answer is over a certain threshold, then it'll actually return the answer. So you could, if you had data to train a model like that, you could use those kind of principles here. Or you could have some kind of post classifier that, given your question and your answer produced from an open domain question answering model, could then say, actually, I'm going to pretend I didn't respond because I don't think this question should be answered. But yeah, again, that's maybe something it feels like a data problem to me, that you could come up with the solutions. We just maybe don't have the data set up in that way. But yeah, that's an important point for actual like practical systems.
Yeah, so that's interesting. So your answer is very close to the approach that we went with, which was we made a Albert Einstein question answer bot, and we actually trained it. We had a large corpus of hand-built question answers that were in the voice of Albert Einstein, but to deal with the problem of the false positives, I actually trained the system against a large corpus of other question and answers from like Jeopardy and other sources that have nothing to do with Albert Einstein, and I labeled them as basically unrelated. So if there was a match against an unrelated topic, that was how we knew we needed to try to find a gambit or ask them to rephrase.
Mm-hmm. Yeah, that's good. That's a great way to go about it. Sort of sampling from some other different distribution, or trying to detect if your question is in distribution or not. Then they call it like a positive unlabeled problem, maybe, that you know what your positives are, but you don't really know what your negatives are. So you can just like sample from stuff in the wild and assume they won't be positive. So they assume that random questions that you sample out in the wild won't be from Albert Einstein, in Albert Einstein's voice, for example. Yeah, cool. Nice.
Thank you.
Thanks. Is Rajat on the line, or should I?
Go ahead and answer it.
Okay, cool. So question is, during the training phase for generation task, do you have gold statements to generate for every given input? And is the input generated from document within the FICE index during the training phase? During the training phase for input for generation tasks, do you have gold statements? Yes. Yes. So what we have is say like a question or an input, and then we have a single gold output generation. That's all we have. That's what we assume to have. And the model, it learns to retrieve documents in such a way that it will do a good job of generating those output sequences that we supervise it on. So that's, I guess, the first part maybe cleared up a bit. Is the input generated from the document within the FICE index? So the input is something that the model receives. So it's something that you say, like, give it a test time. So that's not coming from anything, that just comes separately. But then what we do is we retrieve documents from the FICE index, and the document is then given to the generator as extra input. I hope that helps. Oh, sorry, there was a correction. Gold statements generated for every input. I'm not sure I understand the second part of your question, maybe. So maybe send me an email after, and we can discuss, so we can move on. Cool. Okay. So I'm going to move on to the next one. Would it be possible to answer questions that need to extract answers from more than one document in the top K? So I think we touched on this a little bit, but it's worth reiterating it. So yes, it's possible, as long as those documents do end up in the top K. So for the Jeopardy generation stuff, we saw that RAG token was better at generating outputs, because often for Jeopardy questions, there are two facts in them, and those two facts often live in two different documents. And so, like in that example, I laboriously went through about Henway and the book titles. The book title facts were in different documents, and the model was able to use one document for the first fact and use the other document for the second fact. Now, is that exactly the same thing as what you're asking? I think you're asking whether you can only infer an answer from using two documents at the same time to produce a final answer. And in theory, you can do that for either for RAG token, but it's not super easy. It's unlikely to happen, basically because in order to do that well, you have to condition on a pair of documents for one forward pass of the model, so they can learn the interaction between the two documents so it can extract the answer. And that's something that actually RAG models aren't that good at right now. So you need to think about, instead of conditioning the generator on each document independently and producing an answer and then marginalizing, you want to think about doing this like fusion between the documents earlier, this like information fusion across documents. And that's something that people have maybe started to address. There's a recent paper came out like a couple of days ago from colleagues in FAIR, Gauthier Izekar and Edouard Grave, and they look at a similar approach to RAG, where the documents are used in a slightly different way and it produces better results. So instead of marginalizing to kind of combine information from different documents, they basically train a decoder to read from all of the documents at once. That's the quickest way to explain it. And that does perform better. And that would be better at doing things that the anonymous attendee has asked about, that they would be able to better condition from like two documents to extract an answer that was kind of implied from information in two documents rather than kind of mentioned in two different parts. That was a long-winded answer to the question, that the answer is maybe, but not always. But work does exist that will do this now. Okay, cool. So next question. Did you try it on translation or summarization or some other text generation task? So that's a good point. We thought about doing it for summarization, but the thing we wanted to emphasize in all of the data sets we looked at was this kind of knowledge intensive component. So translation, in theory, only requires a thorough knowledge of the language itself rather than facts about the world. So, I mean, that you can argue, but in essence, translation, all of the information required to translate a sentence is contained in that sentence. So you just have to take that sentence and rewrite it in a different way. You don't necessarily need to retrieve a bunch of related evidence in the same way that for a question, you need something to go from in order to produce an answer. So that's why we kind of stayed in this kind of question answering, question generation, fact checking kind of space, because they are very knowledge intensive, and that's kind of something that seek-to-seek models themselves don't do well in. Whereas something like translation and summarization, you already get amazing, like superhuman results on using pre-trained sequence models for translation and summarization. So you could try it, but I doubt it would work better than just a normal BART model or XLM or whatever trained to do that task itself. Okay, moving on. With an explosion of NLP models, BERT, XLNet already seem outdated. Do you think industry is a better option than academia for SOTA? Yes. Unfortunately, if you want to chase, enormous SOTA results for like a ton of different tasks, industry is an easier place to do that. But that isn't the most important thing in NLP research. So I think the most interesting works I see usually come out of smaller labs or a kind of collaboration between industry and academics. Often when you're trying to think creatively, I think this is a general thing, constraints can make someone much more creative. So I think it was David Bowie. I don't know. There was some like famous 70s rock star. For each album, he would force his session musicians to not use certain like notes or scales or keys or like certain things or like in their lyrics, and that would force them to be even more creative, and they'd come up with better ideas as a result. And I think that's definitely true in NLP right now. Like it's very easy just to throw a ton of GPUs at a problem and like brute force your solution out, and you'll get great numbers, and like hooray for you. Not to specifically attack OpenAI, but I for one aren't that interested in GPT-3 for that reason. It was obvious that that would happen, as in you would get this mad result out of GPT-3. Everyone knew it was there, just no one was like, okay, well, they'll do it, so we don't need to. And like, I don't think it changes the field that much, other than like saying, okay, now we know exactly how well it works if you train a 500 billion parameter model or whatever it was. Someone will do that, and that's great and good for them. But in terms of like moving the field forwards, I think like smaller labs play a massive role, and actually all like new things will come from there. And in the end, you don't want to have to throw enormous energy and compute for every task you want to do. So ways of getting near SOTA, or like doing getting good results in a way that uses the smallest amount of compute, or in the way that has really nice properties, maybe in terms of explainability, or like correlation, or like is well calibrated so that you can like control the model very well. Those are things that we aren't super good at right now. And those are things that are really important for adoption all over the place, for everything. So I think that, you know, if you want to just like push up numbers on data sets, yeah, like having a huge amount of compute is useful, but I think that's far from what we should be aiming to do as a field. Like just getting better numbers. Better numbers for me are a result of better modeling, better approaches. So like when you start to attack a problem, you shouldn't look to get SOTA numbers immediately, and they might happen if you have a really great approach that you can then maybe, if it needs it, throw a ton of compute at the end. Okay. Cool. So I was supposed to ask if people wanted to answer live. Okay. Anyway, so Gabriel's question was encouraging to hear that updating the knowledge corpus is relatively easy. I think this implies that you could ask the question asker for more input documents, encode them, index them, and use them to answer the current question, kind of like conversational QA. Is that true? Yeah, in theory. The trouble is like encoding the documents, like large scale documents take a long time to encode, and like building those indexes take like a day or so to build, and the inference takes like a second or so. So you could definitely use it if they were able to provide you like a small number of documents. So that's an interesting way to attack something like conversational QA or chatbot like stuff, that you could imagine that you have maybe two sets of knowledge store. You have the big one that's built off Wikipedia, super expensive, and you retrieve contextual information from, and then maybe more like a more lightweight one, where that just contains like information about a user or information about the current thing you're talking about, and maybe that's user inputted, like you say. So like imagine like an application where someone's talking to a chatbot, and the chatbot's like, okay, can you give me your emails, or like, and I'll do something with them. And so that person might upload some emails, and then you embed them and build this little local knowledge source that the model can then retrieve from, and use some kind of combination of the big Wikipedia index that knows a lot about the world at large, and then the smaller personal index that knows a lot about the user, and then that can work. So yeah, I think that's a cool idea. Yeah, I think this is quite a flexible approach, so you can imagine extending it in all kinds of different ways. Thanks for the question, Gabriel. And then I might need to ask Catherine to elaborate on her question. Which state-of-the-art model were you using? I don't know the context of that. So feel free to either ping me on email or add a clarification under, but I'm going to move on for now.
Let's take just this one more, given the time that we've been going.
Okay, cool. Okay, so Seth's question, what advice would you give to a young practitioner after the first year starting to get a handle on ML, NLP? Cool. So it's quite funny because I consider myself to be a young practitioner because I'm a PhD student and usually surrounded by people who are far more senior and more experienced than I So I guess it depends what you want to do. Like if you're trying to get a job in industry, or you're just a hobby and you want to build your skills, implementing things is always like really good. Playing with things, getting an intuitive understanding of how things work. So maybe not training models to do really well, but understanding them and playing with them in notebooks is really important. Knowing your tools quite well is useful. So like a lot of people use Hugging Face transformers. I think that's an excellent resource to play with like deep NLP things. In terms of machine learning, try and work up from basics. So it's cool to play with these enormous neural models, but having a reasonable good like grasp of NLP, of like probability theory, and then like basic machine learning things like what is logistic regression, what is the softmax, this kind of stuff is really important. So make sure you don't neglect the fundamentals. And if you see something you don't understand, try and teach yourself about it rather than say, okay, I'll just ignore that bit. Because you won't grow quickly unless you are constantly building out your foundation. Yeah. I guess that's it. And I see Catherine's responded with in your benchmarking. I still don't know which task. So like the state of the art model changes on which task it is. I guess you can refer to the paper. It's all cited in there, Catherine, if that will help you. Okay, I think we've got 1 minute left, so that's about right to wrap up.
Yeah, any further remarks?
Nothing from me. I think that was really fun. Thanks for the questions. They were really interesting to answer. Usually I don't get that much feedback, so it's good. In academic talks, you might have one question and then everyone like be a dead silent room. So that was cool.
You're competing against the academics this week, but anyway.
Yeah.
Yeah, NLP world. Well, thanks very much, Patrick, for this talk. I will be posting the video probably within a matter of a few hours after it's done processing to the NLP XING YouTube channel. And we did have a question whether you'd separately make your slides available. If you do want to do that, best if you could post them somewhere and then send me the URL and I'll get the URL out for wherever on the cloud that they're posted. So once again, if anyone in the audience would like to give a NLP meetup talk, I posted my email address in the chat, and thanks everyone for attending.
Yeah, thank you very much for listening.